Hey guys, welcome back for another chemistry lesson. This video is about wave characteristics and the electromagnetic radiation that we talk about in other videos about the electromagnetic spectrum. So, first and foremost, light is a wave, sometimes. It is a form of electromagnetic radiation, which means that it has perpendicular oscillating waves that intersect at their nodes. You can see that here. So we've got one wave that represents the electric field component, and then another wave that represents the magnetic field component, and they are always at right angles to each other. An electric field is a region where an electrically charged particle experiences a force, and a magnetic field is a region where a magnetized particle experiences a force. So electromagnetic radiation has both components here. All electromagnetic waves move through space at the same constant speed, which is the speed of light. You should probably go ahead and get this number stuck in your head. It's 3 times 10 to the 8th meters per second. That's very, very fast. All right, so the speed of light is so fast that it's essentially instantaneous, right? And other waves that we are familiar with, like sound waves, travel a lot slower. So that's the reason why whenever you are watching a thunderstorm, you can see the lightning immediately, but it takes some time for the thunder to get to you. So for every 5 seconds that it takes for the thunder to get to you, approximately, it's a little less than that, but approximately for every 5 seconds it takes for the thunder to get to you, that's 1 mile away that the storm was, or that the lightning strike was. So let's talk about waves so that we can understand this. Right? First, the amplitude of the wave is the height of the wave, and it is measured from the center point of the wave. I don't know why that was so hard for me to say, but it's from where the nodes are, the level of the node, to the crest, which is the top, or the trough, which is the bottom. And our amplitude, when we're talking about electromagnetic radiation, is a measure of the intensity of the light. So the bigger the wave, the taller the wave is, the brighter the light is. Then wavelength is measured from it's the distance between two exact points, like next to each other. It could be any point on the wave, right? But it's easiest to measure from like peak to peak or from trough to trough. But the idea is two neighboring waves, you're going to measure the exact same place on those two neighboring waves. And then that distance is your wavelength, which we represent with this Greek letter lambda. Then we have the frequency of waves. It's not actually a V, but it looks like one, and for your purposes, if you're writing it, it's just a little fancy curved V. It's the Greek letter nu. But the frequency is the number of waves that pass a point in a given period of time. So, if I'm talking here, if I've got 5 waves that pass this point every second, then that's my frequency. And so, the number of waves that pass, we call that the number of cycles. And the unit that we measure that in is hertz, or cycles per second. So 1 hertz is 1 per second. I know that sounds weird, but anyways, we measure it in hertz. So the total energy in a wave is proportional to the amplitude of the wave and its frequency. So if I have a really big wave, but I get very few of them, that's going to be less total energy than really big waves and a lot of them. Right? Hopefully that makes sense. The larger the amplitude, the more force the wave has, and the more frequently the wave strikes, the more total force there is. So, for waves that are traveling at the same speed, like electromagnetic radiation, the shorter the wavelength, the more frequently they pass. I hope that feels like common sense to you. But what that means is that the wavelength and the frequency are inversely proportional, because the bigger the wave is, it can't get so many by as if we had a shorter wavelength. So because the speed of light is constant, if we know that wavelength, we can find the frequency and vice versa using this relationship. All right, so just kind of to put all that together, our different wavelengths give us different colors of light. Longer wavelengths have a lower frequency, as you can see here, 2 waves versus 1, 2, 3, 4 waves here, right? So shorter wavelength, higher frequency, different color light. And then also different amplitudes give us different brightnesses. So very tall waves will give us bright light, very short waves will give us dim light. And now to talk about color. So the color of light is determined by its wavelength or its frequency. You can use either one. And the thing to know about white light, which is what we typically see, is that it is a mixture of all the colors of visible light. So if you have ever been in an art class and you mix all the paints together and they make black, light is the opposite, right? And visible light is a spectrum in the Roy G. Biv direction. So Roy G. Biv is the order of the colors. You guys have seen rainbows, right? Red, orange, yellow, green, blue, indigo, violet. And our different colors of light are no different on the spectrum, right? So when an object absorbs some of the wavelengths of light, what it does is it reflects others. And the reflected light is what we see. So in the case of this woman's sweater, we're getting white light, meaning all of the colors onto the sweater, and then the sweater absorbs everything except for the red light, which is reflected, which is why the sweater looks red to us. Now, light and other waves also undergoes what we call interference, which is the interaction between waves. And there are 2 different types of interference. We've got constructive interference and destructive interference. So constructive interference happens when the waves interact in such a way that the waves get bigger when they add together. And we call that being in phase. So in order to be in phase, you have to have sort of the same part of the wave interacting. So here we've got peak and peak, trough and trough hitting each other in the same places. So what that means is our waves add together and we get a bigger wave. Likewise, destructive interference is when our waves are out of phase. So our peak and our trough are what's interacting. So peak here, trough here, and they cancel each other out. Now, it doesn't have to be completely canceling out. It can just be we get a smaller wave, or it can be that they completely cancel out. It just depends on the waves and how they're interacting. But we call that them being out of phase and destructive interference. Our waves can also do what's called diffraction. So when traveling waves encounter an obstacle or an opening in a barrier that is about the same size as the wavelength, they bend around it. So that's diffraction. Traveling particles do not diffract. So think about it like a tennis ball going through a hole, right? It's not going to go through the hole and then magically hang a left, right? Particles don't do that. Waves, however, do that. The diffraction of light through 2 slits separated by a distance comparable to the wavelength results in an interference pattern of the diffracted waves. This interference pattern is a characteristic of all light waves, and it actually helped us figure out that that light is both particle and wave. Right? So, here's our diffraction, right? If something is behaving like a wave, what we get is these waves come through, we get a bend of the waves, then they go through these slits, and we end up with this overlap of our waves. So where the waves add together, we get these bright spots where the waves cancel each other out. We get these dark spots. So this is an interference pattern that you would see with the two-slit experiment. So again, if they are canceling each other out through destructive interference, we're going to get a dark spot, as shown here. And then if they are adding together for constructive interference, they're going to give you a bright spot, and that's shown here.